Hello, and welcome to the second lecture covering the second section in Chapter 7, Introducing the Solar System. In the first video for 7.1, I talked extensively about the solar system. It was a big introduction. We went over each of the planets and a lot of ideas that unite the solar system, a lot of concepts about what planetary science is all about. And we kept actually mentioning that we want general rules to cover the solar system. And that's what we're going to talk about in this section, is that the idea that there are patterns in the solar system. It is not just a list of facts. Instead, there are some big ideas that help us understand it and give us expectations of what other solar systems should look like besides ours, how things would have formed, why they formed, is how unusual certain phenomenon are, or are they typical? If we look at a planet that is, orbiting in a certain way, should we think like, oh, wow, that's a very rare occurrence, or no, that's exactly what science tells us, is most likely to happen. So those are the ideas, right? And humans are good for humans are good at looking for patterns, and here we go, looking for patterns. Now, this is a much shorter section. We're just going to reinforce the importance of those patterns in the solar system. So let's get to it. Right, we have one question we're really going to answer in this section, and that is, what features of our solar system provide clues to how it formed? Okay, so we've seen this figure. Again, I would highly recommend watching the first video. And this shows a ton of information about the solar system, all the orbits and relative distances and sizes on different scales and distributions of comets and asteroids. So, right, what's going on? How do we decipher so much information about the solar system? Okay, well, one thing is the dominant pattern of motion. All right, all the large bodies in the solar system orbit in the same direction and in nearly the same plane. All right, can't stress that enough. Flat solar system for the most part, just a couple degrees of variation, everything orbiting in the same direction, which is, by the way, when viewed from above. Okay, so looking above the solar system plane, everything would be moving counterclockwise. All right, and on top of that, all the rotations of these bodies on their own axes, moons, the planets themselves, almost exclusively rotating also counterclockwise. Do you remember the one exception? If you watched the first video, there may have been a planet that stood out as that makes us say most, and it indeed is Venus, which has a retrograde rotation because it's essentially upside down. It is spinning clockwise on its own axis, although it is still, of course, orbiting the way we'd expect in the counterclockwise way. All right, so take a look. You can actually see it right there, right? See the exception with Venus? See how it is spinning clockwise if you look at the arrow? Whereas every other planet, Mercury, Earth, Mars, you get the idea. And then when you go out further in the solar system, everything is spinning that way. Except for this, what's going on with Uranus? Well, Uranus is the other partial exception. It's tipped. See, that's why it's drawn this way, right? It's not, if we're looking down, it's not flat. It's the only one that isn't a circle because it's exactly tipped on its side. Okay, now other big idea here, all right, so really this section is all about just like what are the takeaways from the chapter as a whole. Well, that's that there's two types of planets. Okay, so there's terrestrial and Jovian. So if you think of any overall pattern for the solar system, remember there's two types of planets. They're even divided by the asteroid belt. There's an actual dividing line. By the way, the asteroid belt is not like a dense belt of rocks. The distance between rocks is thousands of kilometers, tens of thousands of kilometers on average. Most rocks are quite small. If you're in any one part of the asteroid belt, it would just look like normal space. It'd be very unlikely you'd even see an asteroid. So just to, in terms of misconceptions about the asteroid belt. Regardless, going on to the two types of planets, right? As we talked about before, terrestrial planets are small in mass and size, like Earth. They are all close to the sun. They are made of metal and rock, all right? And they have few moons and they never have rings. Jovian planets, on the other hand, are large in mass and size, sometimes hundreds of times larger than the terrestrial planets. They are all far from the sun. They are not made primarily of metal and rock, but primarily of gas. Hydrogen and helium in particular, and compounds of hydrogen and helium with other elements like oxygen and carbon and so on. And they all have rings and lots of moons. Okay, so, right, more summaries, right, going into, this is, I guess, all the same information, right, yeah, but in a nice table for easy reference. On top of that, what's the other kind of leftover part of the solar system? How do we sum up the entire solar system? Well, we can't forget asteroids and comets. They make up a tiny, tiny Let me stress that, tiny percentage of the mass of the solar system. Because recall that the mass of the sun is 99.9% of the mass of the solar system. So that means that all the planets share 0.1% of the mass of the solar system. And you can guess that the asteroids and comets are going to be having a similar relationship in terms of how much mass they make up compared to the planets, which is to say that all the asteroids and comets in the entire solar system make up well less than 1% of the mass taken up by the planets. All right, even probably compared to the terrestrial planets, right? That might be, a little too conservative, but certainly compared to the Jovian planets. So if you think about it, that means that it's like just a tiny, tiny fraction, like a millionth of a percent compared to the mass of the sun. But despite that, which almost seems an argument to say, why should we care about them? They're so important. They're so important for understanding, evolution of life in terms of large impacts, that happen here on Earth, like the one that wiped out the dinosaurs. There's important for just the way that planets have evolved over time. A lot of the interesting phenomenon we see, like knocked over planets like Venus and Uranus, or our own moon, were probably caused by large impacts. And they continue to renew amounts of H2O and different elements. And scientists are interested in them because they also represent a way to study the primordial solar system, because they're leftovers. So they have the exact composition that was in the mix, in the formation of the solar system before our sun even became a star, before fusion even began. So it's like looking back in the time. It's like archaeology, but taking a sample from an asteroid. So there's so many reasons that are fascinating, and there are trillions of them, at least as far as comets are concerned. So the number of individuals is huge, right? But some of them are just a few hundreds or thousands or tens of thousands of kilograms in mass. So not anywhere close to the size of planets, right? The Oort cloud is where most of the comets are. It's this incredibly distant cloud at the very edge of the gravitational influence of the sun. Way out there, that's where mini comets, the majority of comets are thought to come from, taking very, very strange orbits as they almost fall in towards the sun, but then slingshot around it, what's called a incredibly eccentric elliptical orbit. But what's interesting is we can't confirm directly the existence of the Oort cloud, because it was too small to, the objects, the comets, are too small to pick up with a telescope, even though, they're relatively close, much closer to other stars, of course, but they're so small and so dim, right? How much light is there out there, and how much light would they reflect? And we can't, bounce radar off them or confirm their existence exactly. And we've never sent space probes anywhere near that far. There are currently space probes leaving the solar system that have passed out into this region called the Kuiper Belt, which is the region of comets again, that is just beyond the orbit of Pluto and stretches for, basically billions of kilometers, which are mini astronomical units, because an astronomical unit, Earth's average distance from the sun, is 150 million kilometers. And so the Kuiper Belt is many astronomical units thick. This, this belt like here shown almost like a ring. And that part of the solar system will take these space probes that I mentioned, like the New Horizon space probe that took pictures of Pluto, which we'll talk about in the next video in the last section of this chapter. Well, they will take decades, if they continue to operate, to get out of the Kuiper Belt itself, and even then it would be a long trip to the Oort cloud, or just the very edges of the Oort cloud, in order to really have any direct confirmation. In other words, it'll probably be the next generation of space probes that are much faster, that would have any chance of actually reaching this part of the solar system and directly confirming it, or learning more about it, right? So it just goes to show that we have parts of our own solar system that are yet to even be confirmed or explored. There could be a ninth planet out there, maybe the size of Neptune, beyond the Kuiper Belt. There's some theories that suggest there could be. So still a lot of mysteries in the very edge of the solar system. All right. So as I mentioned a few times, there's rules and then the exceptions. There's that famous expression that says that that the exception proves the rule, and what that means is that if there is an exception, that means the rule has to have a lot of examples to back it up. Otherwise, the exception wouldn't be called an exception. right? That's how an exception proves the rule. And that's the same case in planetary science. We see a strong trend with, with many samples, many examples of it. And, how many can there be when you only have, 4 terrestrial planets? Well, you at least have maybe 3 out of the 4, right? With the Jovian planets, the same sort of thing. You have 3 out of the 4. And if 1 out of the 4 is acting completely different, isn't seeming to follow the same rules as the other 4, maybe there's a good explanation for that. Maybe, it's not just random chance. It's because something had to have caused it to be different. All right. So, for example, Venus spinning upside down, definite exception. Why? Right? Maybe got knocked upside down by a giant collision. Right? Again, Neptune. Right? Now, some people will say, and it's a kind of an ongoing joke, that astronomers will, especially in terms of solar system, research, solar system astronomy, that everything like this, every exception to the rule has a best case, best hypothesis, most popular theory is something smashed into it. So, it's like, well, maybe that's too easy of an explanation, but also that it tells us something about what the early solar system looked like, that there was a certain likelihood of giant collisions. So instead of dismissing it as saying, oh, well, there's the same, a theory for all these exceptions, maybe just, we should think of it as a very interesting pattern in itself, that these giant collisions were, so important, but now they don't occur anymore because they were all taken care of, right? Once they happened, they were once and done. All right. Now, our little special topic to get near finishing up this section is an interesting idea that involves the transit of a planet in front of the sun as a very accurate, if done, with modern techniques, way of measuring a distance to that planet. And this is so important when we start talking about how scientists know the distance, how astronomers know the distance to distant objects outside our solar system. How the heck do astronomers know the distance to stars? How do they? Because you can't bounce a radar ray off a star that's hundreds of light years away, because the signal would take hundreds of years to travel there, 100 years to come back. It would get disrupted along the way, scattered along the way. So you can never directly know how far a star is, can you? Well, turns out you can, based on some geometry. All right. So the idea is we know exactly the distance between points on Earth. Okay, so follow me on this geometry here. Okay, then we're going to carefully observe during a transit. That's when the planet, like Venus or Mercury, passes directly in front of the sun. And that doesn't happen every time in our respective orbits between, Earth and Venus, for example, because they have their slight tilt between the orbits. All right, so our orbit is not exactly lined up. It's a few degrees off from Venus's. So it's only every few times that our orbits cross, or that Venus laps us, that, well, we have this event where we actually see Venus go right in front of the sun. Okay, it actually recently happened with Mercury just a couple of years ago. Okay, so we're gonna then, as the planet Venus transits in front of the sun, we can image it. We can directly see it as a little black dot passing in front of the sun with the right lens on a telescope. Well, what we can then do is we can measure that angle of the difference in some amount of time, the path that it takes, and then measure the same angle here. So that means using geometry, we've got these 2 triangles, and then we can calculate the side of the triangle, and that will tell us the distance. I'm not trying to, give us the formula here or anything. I'm just explaining the logic behind it. So it just comes down to the angles in trigonometry, and now we know this distance, okay? Because we were able to measure the other relevant distance exactly, okay? So to reiterate, you measure the apparent position of Venus on the sun from 2 locations on Earth, okay? 2 different locations, you know the distance between them, okay? So that means you know the angle, you know the base of the triangle. All right, using trigonometry to determine Venus's distance from the distance between the 2 locations on Earth, okay? That's going to give you this length right here. Nice, right? Now, before I actually kind of showed it as the hypotenuse, but they're basically exactly the same as each other, because it's such a long angle, right? Such a small angle. Okay, so what have we learned in this section, right? Well, we basically talked more about patterns, right? We talked about the fact that the motion of the large bodies are all in the same direction and plane. There are 2 main planet types, terrestrial and Jovian. There also is, don't forget, asteroids and comets, separate things. One's rocky, one's icy, right, which is part of the solar system. And there are notable exceptions, such as Uranus, Earth's large moon, okay, which we talked about before, but not again in this section, and Venus, okay? There's even some moons that are retrograde. The moon way out in Neptune, Triton. Triton is another exception to the rule, a famous one. I'd say that probably those are the big four. Okay? All right, well, that's it for that section. It really was very much a summary, which hopefully makes it a useful kind of way to look back on this material, because it's a lot as we get started with the solar system. But enough said on that. Thank you so much for watching. I hope this video has been interesting and informative. Come back next time to watch the video for the last section in Chapter 7 about spacecraft exploration in the solar system. Bye for now.